we're going to be talking today about the derivative as a function. We've already talked about the derivative at a particular point by letting a be that certain value. And now we want to get the derivative at any point, not just at a particular point like a equal 5. So we want to redefine the function of the derivative. So we want to define it as a function. In other words, if you put in a value, it will tell you what the derivative is at that point. And remember, the derivative is really slope of the tangent line. So that's what we're talking about, is finding the slope of the tangent line at any point along a particular function. Now, the two definitions that we use to find the derivative as a function are the h version and the delta x version. The f of x minus f of a over x minus a, that one we kind of reserve for finding the derivative at a particular point, all right? So the two that are best for finding the derivative as a function, not at one point, but at all possible points, are these two right here. And they're essentially the same. The only difference between them is an h and a delta x, where those are interchangeable concepts, because h is that small amount that you move over in the x direction, all right? So when we're talking about this particular function, if I were to draw a picture and I had a graph and this were x, this would be x plus h, or x plus delta x, where that distance between them is h, some small amount. And we're talking about allowing h to go to 0 so that we can find the slope of the tangent line at any particular point x, all right? So in other words, instead of finding f prime at a, we're going to be finding f prime of x, where the variable will stay in it. The variable x will stay in it. So we use these two versions, but without a, with x instead. All right, so we're going to start with x squared, and then we'll also learn the easier way of doing the derivatives today. And after today, you'll be like, oh my gosh, we did all that work with the difference quotient and I could have just done this very simple thing. Yes, but on the exam, I will ask you for all three definitions of the derivative. And then I will ask you for the hand waving definition, slope of the tangent line, and I will ask you to apply it. So I could ask you a problem exactly like example 1, find the derivative using the definition, and you have to use the definition. So first we'll find f of x plus h. Remember, you take the function, you take out the variable, replace it with open parentheses, and then replace what was in the parentheses with x plus h. When you multiply that out, you get 3 terms, which looks like that. Then we can put it into the difference quotient with the limit as h goes to 0. And we have f of x plus h as x squared plus 2hx plus h squared. Then we subtract f of x, which is given to us as x squared. And then it's all divided by h. This is basically slope of the secant line, y1 minus y2 over x1 minus x2, where the difference in the x values is that h. The x squareds cancel. We get the limit as h goes to 0 of 2hx plus h squared. Then we can divide each one by h. Make sure you individually reduce those fractions because they're both divided by h. And that gives us the limit of 2x plus h. And as h goes to 0, you can substitute 0 now for h, and you get 2x. Notice that this is a function, not a number. So what we found is that f prime of x is equal to 2x. So on the graph of x squared, if I want to know the slope of the tangent line at any point, I can find the slope of the tangent line at any point by plugging in that point into 2x. So let's say I want to know what the slope of the tangent line is at 5. I plug 5 in and I get 10. So the slope of the tangent line at 5 is 10. All right. So that gives me the slope of the tangent line at any point. All right. Let's repeat the process on this next example, which is the square root of quantity 2x. Remember your function notation. F of x plus h. You take out the variable x and you replace it with empty parentheses. Then you substitute x plus h into it. This will give us the square root of 2x plus 2h all under the radical. And then when we find the limit as h goes to 0, this gives me the square root of 2x plus 2h minus the square root of 2x all divided by h. Now, if I tried to plug in h equals 0, I'm going to get 0 in the denominator and 0 in the numerator. So it leads to that indeterminate form of 0 over 0 if you plug in. So what might I try to find this limit? What would be the next step?
Would you multiply by the conjugate pair?
Yep. Multiply by the conjugate of the part with the radical. So I'm going to multiply by radical 2x plus 2h plus radical of 2x. I'm trying to get that hidden factor that's causing 0 over 0 to come out so that I can cancel it. So I multiply by the conjugate divided by itself. And that's going to give me the first term times itself, just lifts off the radical, and I get 2x plus 2h. The outside gives me a positive product of the two radicals. The inside gives me a negative product, so they cancel out. And then I have the square root of 2x times itself with a negative, so it gives me minus 2x. I leave the denominator square factored because I'm hoping to reveal that factor that's causing the problem. And then in the numerator, the 2x's will cancel. And that leaves me with 2h in the numerator. H is a factor in the denominator, and then the radical term from the conjugate. And then the h's cancel. So the whole point of doing the multiplication by the conjugate was to get this factor of h over h to come out so that we could see it. So now we can cancel the h. And now when we plug in, we should not get 0 over 0. So when I plug in this time, I get 2 over the square root of 2x plus 2 times 0 plus the square root of 2x, which is equal to 2 over the square root of 2x plus the square root of 2x, which is 2 over 2 square roots of 2x. The 2's cancel, and I get 1 over the square root of 2x. So this gives me an expression for the function of the derivative, 1 over the square root of 2x. So let's say I wanted to know what's the derivative at 4. Then I just plug in 4 in for x, and that gives me 1/4. All right. And then I can use that to find the slope of the tangent line at that particular point. To find the slope of the tangent line at that point, I have to find f of 4, which is, what is f? Square root of 2x. Square root of 2 times 4, which is equal to 2 square roots of 2. So that gives me the ordered pair 4, 2 square roots of 2. So the tangent line at 4.
Did you have a question?
Should be.
Can you hear me?
No, what'd you ask, Sean?
So I just need to know where did you get 1/2 square of square
Where did I
square root
get the
of
1/2 square root?
yeah of x?
From up here. Right here, I had two of them added together. So that gave me 2 square roots of 2x. And then these twos canceled. And I got 1 over the square root of 2x.
Yeah, I got that one. So what about that one? 1/2 square root of x.
This one here.
No, the first one. Yeah, that one.
That one.
Yes.
Okay. I just picked it at random. Yeah, I just picked it at total random. I have to turn my volume up. You're a little quiet. Yeah, I just picked the value of 4 at random. If we wanted to know what it was at 4, we'd plug in 4. If we want to know what it is at 8, we would plug in 8.
Okay.
So this is like a different problem, if you will. All right.
Oh, okay.
So then this gives us y minus 2 square root of 2 equal to 1/4 x minus 4. So that would be the tangent line at x equal to 4. All right. So you can use the formula to find the derivative at any point. If you want the derivative at 4, you just plug in 4. If you want the derivative at 2, you just plug in 2, and you can get the derivative anywhere. It's a formula. All right. Okay, let's try this next example. And I think I'm going to return it onto the next page. There we go. All right. So on this page, we've got the problem x plus 1/x. Now, x plus 1/x can actually be written in a rational function form. And I would probably do that first. So that's x squared over x plus 1/x, where I got a common denominator by multiplying x over 1 by x over x. And so that gave me the common denominator. And this becomes x squared plus 1/x. And this is the same thing as f of x. Any questions about how I got the new equation for f of x? Okay. All right. Then the next thing, and the reason I would do that is it's difficult to deal with ones that are mixtures of fractions and not fractions. It's easier if it's all a fraction or not a fraction. So then we're going to find f of x plus h. We're going to take our function and we're going to open up holes wherever we have the variable x. So it looks just like our function up here, something squared plus 1 over the something. And we're going to put x plus h into the holes. So this is going to give me x squared plus 2hx plus h squared plus 1 over x plus h. Nothing can cancel because the x plus h is joined together with addition. And so either all of it goes together as a group or none of it goes. So now the next thing we want to do is plug this into the difference quotient to get the derivative function, which is the limit as h goes to 0 of f of x plus h, which is x squared plus 2hx plus h squared plus 1 all over x plus h minus f of x, which is this up here, right here. So we get x squared plus 1 over x all over h. Now, if we were to put in that h is 0, if we were to plug in h is 0, we're going to get the indeterminate 0 over 0 form. And you get to where you can kind of tell that just by looking. anything with h would drop out and you get x squared plus 1 over x minus x squared plus 1 over x. So that goes to 0 and h goes to 0. So you'd have 0 over 0. So since we don't want that, we have to think of what else we can do. And probably what we should do is get rid of the complex fraction by multiplying by the lowest common denominator of all the little denominators. But in order to do that, I need to write the denominator in complex form by putting the h over a 1. So the little denominators that I have are the group x plus h, x by itself, and 1 by itself. So that's what I need for my lowest common denominator is an x plus h group, an x by itself, and then just 1. So I'm going to multiply numerator and denominator by that. So I'm going to put the whole thing in parentheses, and I'm going to multiply by x plus h as a group times x. And if the x at the back bothers you, you can put it at the front. It doesn't matter. It's the same thing. If you want to write it at the front. All right. So we're going to distribute everything in the numerator, but we're going to leave the denominator in factored form because we're hoping to reveal that factor that's causing the 0 over 0. So we're going to multiply out the numerator. So I have the limit, h is going to 0. The x plus h cancels the x plus h in the denominator. So I get x times x squared plus 2hx plus h squared plus 1 minus, and then the x's cancel on the second term, and I get x squared plus 1 times x plus h, all divided by, and I'm going to leave the denominator in factored form. Now, the next thing I need to do is multiply out those terms and see what I can come up with. So if I multiply out the factors, I end up with, let's see, x cubed plus 2hx squared plus h squared x plus x minus, if I multiply these out, I would get x cubed plus hx squared plus x plus h. And then the negative distributes over the whole thing and makes every term negative. So minus x cubed minus hx squared minus x minus h, all divided by the factors h, x, and quantity x plus h. All right, you have to be careful with the algebra to make sure that you get the right sign on all the terms and that you distribute correctly, because otherwise what's supposed to cancel won't cancel. All right, so I've got an x cubed and a minus x cubed. So they're going to cancel. I've got a plus 2hx squared and a minus hx squared. So that's going to give me a 1hx squared. So I've taken care of that term and that term. Oh, nope, I have not, because I lost the h. No, that's h squared x. All right. I don't have any of the other h squared x terms. So I have a plus h squared x, and that takes care of that term. I have a plus x and a minus x, so they cancel. And then I've got a minus h. All over hx, x plus h. We still haven't found the factor that was causing the 0 over 0, but there's an h factor in the numerator. So you factor it off the terms of the numerator. Right? So what I've done is I've taken the h from the numerator and factored one of them out of each term, which leaves behind x squared plus hx minus 1. And that reveals the hidden factor that was causing that indeterminate 0/0 result. Now I can cancel the h over h. And now I should try to plug in the values again and see if I get a number. Which is going to give me the limit. Well, I guess I don't need to write limit again. I can just plug it in. So I get x squared plus 0 times x minus 1 over x times x plus 0, which gives me x squared minus 1 over 2x. Right? And that is the formula for the derivative at any given point on the graph, the original graph.
Johanna,
Derivative. Yes?
sorry, question. Wouldn't it be x squared in the bottom?
Oh, my bad. Thanks, Juan. I'm sleeping today. All right, yes, x squared. All right, which you could reduce it and split it into 2 terms. I'm fine with it like that, but you could also write it like this. Right? And that would work as well. Either one of those. Okay. Let's take a look now at equivalent notations for the derivative function. There are lots of different ways of writing down the derivative function f prime of x, and we'll probably use all of these except the last two. The last two get used in differential equations. They also get used in calculus 3. So you'll see these get used in calculus 3 when you're doing the directional derivative. All right. But the rest of these, we'll use all of these in this class to represent the derivative function, and they all mean essentially the same thing. So f prime of x is the one we've been using. That's this one right here. We've been using f prime of x, which is this one. All right. But if you drop the x part, you can just write it as f prime. Now, remember that this is the derivative function. And so you can also write the derivative function with a d by dx. So this notation of d by dx means to take the derivative of the function with respect to the variable x. So it's written in fraction form, but it's not actually a fraction, it's an operation. It says take the derivative of the function x where x is the variable, all right? So whatever variable is used in the denominator, that's what it considers the variable in the function to be, all right? So if it had d by dt, then it would be considering t to be the variable in the function, all right? So it depends on what's written. You can also abbreviate that notation by dropping the of x and just writing df dx, all right, which we usually just say like that, df dx. We don't say df by dx necessarily. It's divided by, but we typically just say df dx. Since f of x is really the y variable in a function, we can also write dy dx. This is a very common way of writing it. This is very common. This one is common as well. Actually, they're all fairly common, but this one is especially common. You will see the derivative with respect to x of y of x less often. You'll see this one more often in a differential equations class, which would come after calculus 3. So you would see that one more in Diffie Q. And then y prime and y prime of x, again, you would see these more often in differential equations but you will see them at least once this semester when we do implicit functions. All right. And these are all different ways of writing the same thing, which is the derivative of a function with respect to x. And instead of writing f prime of a, we can use this bar notation right here. And we can write the derivative with respect to x of f, evaluated at, say, x equal 5. What does that mean? It means find the derivative of the function f with respect to x and plug in the value 5 so that you're finding the slope of the tangent line at 5. All right, so this long vertical bar is a way of indicating substitution. So the long vertical bar means to substitute 5 in the result of what you have on the left-hand side. And this is very common notation as well. The d by dx, written in fraction form, but not representing a fraction, and dy dx, these are Gottfried Leibniz's notation. And they're the most commonly used notations for the function of the derivative. Now, when Newton did this, he used a dot and sometimes he used a bar. Mostly he used a dot, but he was not consistent and it didn't have the same meaning. Leibniz's notation allows us to do some manipulation with that notation as if it were a fraction that always works. So we're still using his notation some 320 years later. All right. All right. So when we're thinking about the slope of the secant line becoming the slope of the tangent line, the secant line is delta y over delta x, whereas the instantaneous, which is right here at one single point, that's dy over dx, which is that incremental change, that tiniest amounts of the change in y over the change in x. All right. Okay. And it's the limit of the secant line as delta x goes to 0. So dy dx is equal to the limit as delta x goes to 0 of delta y over delta x. This is where the delta x notation makes a little bit more sense than the h notation. It is a small change in the x value. And when you're looking at the graph up here, what you're talking about is you have this change in x, which is getting smaller and smaller, so that the slope of the secant line is approaching the slope of the tangent line as the point gets closer and closer to the same value. All right. Now let's talk about graphing a derivative function. This is actually kind of challenging, to be honest with you. I have some techniques for you guys to use, some tricks of the trade that will help you to draw the derivative function based on what the function looks like, based on the original function. So we want to think about an original function and what the graph of its derivative would look like. All right. So we're going to start with the curve, the square root of x, and its derivative is 1 over 2 the square root of x. So we're thinking about the function square root of x as being f, and f prime of x, which is dy dx, is equal to 1 over 2 the square root of x. All right. So what does it look like? So here are the two graphs, one on top of the other, and let's take a look and see if we can figure out why the graphs have this relationship to each other. So you want to take your pen or your pencil, and you want to put your pen or your pencil on the blue graph, which represents the original function. So let's start out here where it's a little bit flatter. I've got stuff all over the floor. I need to clean up my space. All right. So we're looking out here, and if I put it right there, I can say that this slope is positive because it's uphill. Remember to read from the left side to the right side. That's how we read a graph. So left to right, it's uphill. It's relatively flat, it's less than 1. So I come down here, notice that at the same point, the value of the derivative is positive, but it's less than 1. Does everybody see that? The value of the derivative is positive, but it's less than 1. Now move your line over a little bit. This is a little bit steeper, not much, but just a little bit. So this is a little bit higher, still less than 1. Keep moving it along the curve. Right about there, it's right about getting close up to being larger. So notice that it's coming up higher, coming across, coming across, coming across. Right about there, I have a slope of 1. All right, it's at about a 45-degree angle. So at that point, the slope should be about 1. As I come around towards the origin, though, notice that the slope of the tangent line is getting really, really vertical. It's going very, very steep, which is going to cause the graph of the derivative to go up, 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 up. In fact, as it comes around to the origin, it goes vertical. Going vertical is going to cause the derivative function to go to infinity. All right. So when the function's tangent line goes vertical, the graph of the derivative goes to infinity. That's one thing you should mark down. All right. When the graph of the function goes vertical, the derivative goes to infinity. It will either be positive infinity or negative infinity, depending on what you're looking at. All right. Okay, let's look at a different function. X squared minus 2x and its derivative 2x minus 2. Now, when we look at x squared minus 2x, I'm going to start on the left side this time. And notice when I start on the left, if I put my pen onto the graph as a tangent line, it's relatively steep and it's downhill. Downhill means it's a negative slope and it's more than 45 degrees, so it's more than a -1. Down below it on the graph of the derivative, I have a value that is very steep, -4, and it corresponds to this point where the slope is very steep and negative. Then as I come towards the origin, notice that the slope of the tangent line is becoming less. All right, it's still negative, but it's becoming less, so it's coming this way. When it reaches this bottom part right here, at one instant, the tangent line is horizontal. Wherever you have a minimum or a maximum on the graph of the original function, you have an x-intercept in the derivative. This is something else you need to write down. When you have a maximum or a minimum in the original function, that corresponds to an x-intercept on the derivative, because the slope of the tangent line goes to 0 at that point. Then as it keeps moving, it becomes a little positive, but it's still very small, much less than 1. So you can see it's positive and less than 1. And then it goes up, up, increasing, 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 increasing. Now, how would you know it's a line? Well, you probably wouldn't know it's a line. You can get the basic shape, but you wouldn't necessarily know it was a constant line unless you looked at the equation of the derivative. All right. So let's talk about some steps to graphing the derivative from the original function. What are the things you need to look at first? The first things you need to locate would be the places where the original function has a horizontal tangent line. These would be your maximums and your minimums. So the tops of hills, these are your maximums, and the bottoms of valleys are your minimums. All right. Those become x-intercepts on the graph of the derivative function. Then starting at the far left, determine if the original function is increasing with positively sloped tangent lines or decreasing with negatively sloped tangent lines. If it's increasing, then you'll want to mark the derivative above the x-axis. The values of the derivative will be positive. If it's decreasing, you'll draw the derivative function below the x-axis. The values of the derivative will be negative. If the tangent line gets very steep in magnitude, then you're going to draw the derivative farther away from the x-axis. The more steep the tangent line is, the further from the x-axis it is. The flatter the tangent line is, the closer to the x-axis it is. As the original function goes to a vertical tangent line, the derivative goes to infinity. Okay, part 4. If the tangent line is approaching horizontal, but not horizontal yet, then it's close to the x-axis. When the tangent line is relatively flat, it's close to the x-axis. If the graph of the function approaches a vertical line, then you're going to draw the derivative approaching a vertical asymptote at the same point. It goes completely to infinity or negative infinity, like in a vertical asymptote. If there's a linear line segment in the graph of the original, and by linear, I mean like a line, right? A part of a line, a straight line. Then this section of the derivative will have a constant value, and it'll be a horizontal segment on f prime, because the slope of a line segment is always the same value. It's a constant number. So if the slope is, say, 3, then it's always 3, right? Constantly 3, right? There are lots of rules. 7. If there's a sharp corner or a cusp on the graph of the original, then there is no unique tangent line, because the tangent line does not exist at corners or cusps. There's no way to draw a unique tangent line on something that comes to a point, so that will correspond to a hole in the derivative. All right. We haven't talked about inflection points yet, but we'll talk about inflection points in just a second. All right. We haven't talked about where they are in the graph. All right. Inflection points are the places where the slope of the tangent line is the steepest. It's in between where it was getting steeper and then it becomes flatter again. These become the maximums and minimums of the graph of the derivative. All right. So let's try some examples like this one. All right. So we're going to start with something that's relatively straightforward, not completely, but relatively straightforward. All right. Now, the first thing we want to notice is there's a corner right here. Does everybody see that? There's a corner on the graph. Derivatives do not exist at corners or cusps. So that's going to correspond to a hole in the graph of the derivative. This part of the graph right here has slope 1. And this part of the graph over here has slope -1. So I don't see the y value marked off. So I'm going to mark off 1. So on this part, it's constantly 1. And on this part, it's constantly -1. All right. Those aren't exactly symmetric, are they? I got it up a little too high. That's a little better. Okay. All right. So again, on a linear line segment, the slope doesn't change. It's a constant value. And that corresponds to a horizontal segment in the graph of the derivative. There's no derivative at the corner, so that's a hole in the graph of the derivatives. On this section, the slope is a constant value, which is -1, so it's going to graph down here at -1. All right. let's look at this one right here. Okay, so we want to figure out what's going on with the slope of the line on this part right here. Now notice right here in this center section, what you're looking at right here, the tangent line is going to go vertical. So when the tangent line goes vertical, the derivative has a vertical asymptote. So I'm going to have a vertical asymptote right here at that same point. All right, so it's going to have some kind of vertical asymptote. Now we're going to start on the left side and we're going to come up. So I'm going to take my pen and it's going to pretend to be the tangent line. Is it sloped uphill or downhill? Well, it's uphill, but it's pretty flat, right? So it's uphill and pretty flat. Uphill means positive, so above the x-axis. Pretty flat means close to the x-axis. So out here, I'm going to put a point like that. Then I'm going to move it along and watch what happens to the tangent line. The slope is getting steeper, but not significantly steeper, but a little steeper. So this has to be coming up like this. Now, when it gets closer to the origin, it really starts getting a lot steeper, and then it really gets steep, and it approaches this, but it always stays slanted uphill. So this becomes steeper, 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 steeper. And if you connect the dots with a smooth curve, it's looking something like that. All right. What about the right-hand side? We're going to approach from the far right, where we're at positive infinity. Again, it's sloped uphill and it is relatively flat. And it stays relatively flat. It gets steeper as I get closer between 1 and 0. Then it starts getting steeper, 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 but it's still sloped uphill. And because it's uphill, it's above the axis. So again, it starts out low. It doesn't make a big change until it gets closer over here to 1, and then it starts climbing very rapidly. Does everybody see that? That's the graph of the derivative from the function. And again, we're not trying to get an exact graph. We're just trying to get an approximation. And this is the graph of the cube root of x. Okay, let's try another one. This is probably a 4th degree polynomial that we're looking at right here. And we want to try to draw the derivative function on this graph. So the first thing I want to identify are the maximums and minimums. So I'm going to pick out the maximums and minimums, and underneath them, I'm going to plot x-intercepts on the derivative. All right. Now, what is an inflection point? An inflection point is where it changes curvature. Where it changes curvature. And we haven't studied curvature yet, but we will be. But we can introduce the idea here. Curvature. All right, so up, down, right there. All right, so what we're looking at is we're looking at a place where it goes from being curved up to being curved down. All right, so we're looking at a place where it was cupped down, and now it's cupped up. That one spot where it changes the curvature, that's called an inflection point. Now, it's kind of hard to eyeball where those are, but you just do the best you can. And as long as it's reasonable, then I'm going to accept it. So there has to be a place where it does that between negative 1.5 and 0.5, because it's cupped down definitely at negative 1.5. And at 0.5, it's already cupped up. So somewhere in here, it changes curvature. All right. So we're looking to see where we can tell that it's no longer cupped one way, but it's cupped the other way. And we're going to put an X on it. Now, you just kind of have to eyeball it. All right. I think it's about there. All right. Inflection points become maximums and minimums on the derivative. There has to be another one over here on the right side. And based on the fact that the graph is symmetric, then the inflection points will be symmetric. All right. Now, what do inflection points become? These become maxes and mins on the derivative. All right, so now we're ready to start trying to draw it. I know you think that's not enough information. I have no idea what it looks like. Okay, no, I don't either, but we're going to figure it out. So we're going to start on the left, and I'm going to put my tangent line pen on the graph and ask myself, is that steep or flat, uphill or downhill? So what do you think? Steep, flat, uphill or downhill? Somebody volunteer.
Steep uphill.
Steep and uphill.
Good. I heard lots of voices saying steep and uphill. Steep is far away from the x-axis. Uphill is positive. So above that point, put a spot far from the x-axis on the positive side. As it gets closer and closer to the maximum, it becomes less and less steep, and eventually at the maximum, it becomes horizontal. That means it's approaching the axis. So it's coming down and hitting here. Then what is it going to do? Once I'm horizontal, do you see how it goes negative? It's now tilted negatively. So it's going to be a little below the x-axis, then more steep, more steep, more steep. It gets pretty steep until it reaches a maximum steepness at the inflection point. So I've got a little below and then a lot below, and somewhere, oops, I accidentally erased it. Somewhere under that inflection point, it has a maximum steepness. So it comes down and it hits. And then what do you think it's going to do? Since that has to be a minimum, it's going to become less steep. It's still sloped negatively, so it's still below the axis, but it starts going back horizontal, which means it's coming back towards the x-axis. So it's coming back up like this. And then on the other side of the axis, it goes a little bit positive, then more positive, and then the maximum steepness is at the inflection point. So we get a maximum steepness again above the inflection point. And then it is going to continue to be positive, but it's flattening out again because it's going to approach that horizontal tangent line where it's going to be 0. So it's got to come back down. It's still positive, so still above the x-axis, but getting flatter, so getting smaller in value. Coming back to here. And then it goes a little bit negative, then more negative, then more negative, then really negative, then wow, it's really getting very negative. All right. In other words, the graph of a 4th degree polynomial, the derivative is a 3rd degree polynomial. All right. We have 2 places where we have a max or a min, so it's got to be at least degree 3. All right. Any questions about how I drew that derivative on there? Okay.
So you're trying to interpolate, I guess, with what you view the slope as on the original graph. and then you're trying to translate that into values that would be the derivative.
That's correct. That's correct. The slope of the tangent line is the value of the derivative at a point. All right, let's take a look at another one. This one has something on the graph that the others did not have. Or actually, this isn't the one I was thinking of, but it does have some things on the graph that the others did not have. All right. First off, it's a piecewise defined function because it's got 3 different pieces and it's got a hole in it. So we know we've got multiple pieces going on here, but it is still a function. We've got jumps in the graphs. We've got a hole in the graph. I think that's basically it, jumps and holes. All right. So the question is, how are we going to draw the derivative? First thing we're going to do is we're going to locate the maximums and the minimums, and those become x-intercepts on the derivative. So there's a maximum up here at -5. So that becomes an x-intercept on the derivative. It looks like there's a maximum here at the origins, or maybe just slightly to the left. So that's going to be an x-intercept on the derivative. It looks like there's another maximum at 3. So that becomes an x-intercept on the derivative. The next thing I want to look for is a change in curvature. The first part of the graph is always curved down. Does everybody see that? It's always curved down. So there's not going to be a maximum or a minimum on this part right here. The second part, on the other hand, has a part where it's cupped up right here on the far left, and then it's definitely cupped down here. So somewhere in between, it changes curvature. And you just kind of have to eyeball it and say, I declare it to be, well, here-ish. That's going to be a maximum or a minimum on the graph of the derivative, a low spot or a high spot on the derivative. The third piece, likewise, is always curved down. So it is not going to have a low spot or a high spot either. It's just going to be continuing in the same pattern. So let's start at the far left and interpret each
I have a
piece.
question.
Go ahead.
So you put an asterisk or an X in there because you said it's because where it's changing slope, right?
Changing curvature.
But it looks like in that it wouldn't change curvature like in the point, like in 5, in the x equals 0. Isn't that where it changes curvature? Because maybe I'm confused with the.
Okay, curvature is where it goes from being cupped one direction to being cupped the other direction. It's that spot. So I'm trying to find where it's curved down as opposed to where it's curved up. And it's kind of hard to say. It could be closer to the 3.
Oh, okay, I got it. So, okay, I got it. We can say like it's where, I don't know, because no, never mind. No worries.
Okay,
Never
Juan.
mind. Just
So it's where it
maybe
changes
gonna
from-
confuse people.
No, that's all right. It's where it changes from being cupped one direction to being cupped the other direction. All right. It's from holding water to emptying water out. All right. So on this part of the curve, it would hold water. And on this part of the curve, the water would fall out. And you're trying to figure out where it changes that in between. It's somewhere in this section. All right. These are not going to hold water, either one of them. They're both cupped down. So we call those concave down. All right. That's the actual term for it. This is concave down. And this is concave up. All right. Up like a cup, down like a frown. All right. Okay. Let's start on the far left and let's interpret each piece. So when I start on the far left, the slope is uphill and it's steeper than 1, but it's not huge. So steeper than 1, but not necessarily huge, maybe a 5. And then it becomes flatter because it's approaching that horizontal. So it's coming downhill and it's going to connect with this spot here. And then it goes a little bit negative because it has to tilt negatively to be curved down. And then it's more negative and more negative and more negative, and then it just stops. So right underneath the -4, it looks like it has a slope down about there. And I just connect the pieces. Notice that what looked like a parabola ends up with a derivative that typically looks like a slanted line. A parabolic section has a slope that looks more or less like a slanted line. Now this one is not just a parabola because it's cupped up and cupped down, so it's going to be a little different. So we're starting at the bottom, but there's a hole here. Notice that these two didn't have holes, so they're going to keep going. So this one keeps going in this direction, but it stops here because that one stops there. So now we want to look at this hole at -4. It would be at the origin because this, oh, I didn't even mark it, did I? I forgot to mark this one. This is also a place where the tangent line is horizontal, but it's a hole. So I'm going to make it a hole in the graph. And then as I move just a little bit to the right, it tilts positively. And then it gets steeper and steeper and steeper, but still positive until it reaches the inflection point. So above the inflection point, at whatever number you think that is, it's going to come up and then it's going to come down because this is the maximum steepness. The inflection point is maximum steepness. And then it has to start getting flatter again because it's approaching a place where the tangent line's horizontal, where the tangent line has a value of 0. So it comes up, reaches maximum steepness, and then it comes down again. All right. Then the next part is it goes a little bit negative, then more negative, more negative, more negative, still very negative until at 2 it stops. So it's going to become quite negative, but it's going to stop when it gets down to here. It just ends, right? Now I need to pick up again at 2, but there's a hole on this part. But I've got to kind of guess what value that is. It looks like maybe a 3, a steepness of 3. So I'm going to put a whole steepness at 3 because it's included down here, so it can't be included up here. It's got to be a function. And then it's still positive, but getting flatter because it's approaching a horizontal. So still positive, but getting flatter and approaching a horizontal means it's going towards the x-axis. Then it becomes a little negative, then more negative, then really, really negative, and then it keeps going negative. So it's going to keep going down like this, but I do have a hole at 4 where there's no tangent line. So it looks something like that. Questions on any piece of that? You guys look a little unsure.
Very. One of the things you were saying was the minimums and maximums or the derivatives graph will be 0 for the y values. Is that what you said?
No, they're inflection points. The x's. The x's become mins and maxes on the derivative.
Oh, Johanna, can I ask you if you can do like 1 in decimals, like put an equation, then derivative, and show us like all the
I can do that. Let
different
me do that
things?
right
I think it will be more clear. I don't know.
now. It might be. Let's try. Okay, you should be able to see my whole screen now. All right, so let me put in a graph for you. Helps any. Okay, so when we're looking at the red graph, do you see how negatively sloped it is? If you put your pen on there, it's sloped really negatively. And as you're coming down, it's really, really negative. So this is a very steep number coming up. And then as it gets right about here, it flattens out for one little instant, reaches this point right here where it changes its curvature. Does everybody see where it changes curvature right there at 1? We have a curvature change at 0, 1, where it was cupped up and now it's cupped down. And do you see how the derivative has a maximum at that spot? So the curvature change is really subtle. So when you're looking at it, it's curved up, this little part, and then this little part is curved down, and then it's curved up again. So you've got a change of it. So let me take a picture of it. I can find my snippet. And then I'll build one. Okay. All right, so let's take a look at this graph so I can draw on it. There's a curvature change right here, and that corresponds to that maximum spot in the graph of the derivative, which is blue. And then it's curved down for a tiny little bit, and then it curves up again right here. All right, so it's curved up again. And wherever it changes the curvature again, which is right about here, we have a minimum again, which is right here. All right. Okay. And then where does the derivative cross the x-axis? Directly above the minimum point on the graph of the original function. I'm going to let you guys stare at that for a minute, and I'm going to create another one that's a little bit easier to see. It'll take me a minute to work it out.
I have a question.
Go for it.
So I can tell where you marked the X's, like where it changes curvature, and I follow that it's either a max or a min, but how do you decide like what the values are?
Totally
Like
at random.
-3 and -5. You just guess?
Yes, you guess. Totally at random. It's not going to be a perfect graph. It's going to be a sketch. So it's not going to be perfect. Okay. So let's see if this one will work. All right, so there's one example. Let me do another one. I'll leave those in here, but I'll put on another one. Okay. So there's that one. And let's pull it apart a little bit. Let's go -10 to 10. All right. There, that's a little better. Okay, and the derivative. There's the derivative. All right. Okay. So when we're looking at this one right here, again, you're just trying to get a sketch. You're not going to get a perfect picture. You're just trying to get the basic shape. So when you look at the original, which is here in purple, it's coming up from the bottom and it's steep and positive. So this is going to be steep and positive far from the x-axis. Then the original reaches a place where it has a maximum, and that's going to be an x-intercept on the derivative. So steep coming down and hitting the x-axis. Then do you see how the original, the purple, is curved down here, but it's curved up here? All right, so somewhere in between, there's got to be a change in curvature. Wherever that change in curvature is, wherever you eyeball it to be, there's a minimum on the graph because it goes from steeper to less steep. So that makes it a minimum. So then we draw this a little below, and then it comes back because we've got this spot right here where there is a tangent line that's horizontal again, and that corresponds to an x-intercept. So it's got to turn around and come back towards the x-axis. Then it goes positive, positive, steeper, steeper, and this goes up, up, up forever. All right, does that sort of help a little bit? A little bit? All right, so let me take a picture of this one.
Okay, so I think I've made sense of two things. The inflection point when we're changing the up of the slope, if you will, are the minimums and maximums of the derivatives graph.
Correct.
And then another constant we have that you just said was the original graph's peaks and valleys are going to be the x-intercepts for the derivatives graph.
That's correct.
Okay.
Yes, you got it. Those two things you can hang your hat on. All right. So the peaks and valleys of the original function are the x-intercepts of the derivative, and the maxes and mins on the derivative are the inflection points on the original. Okay. And I think I'm going to skip that one. Oh, I've already done that one. And we'll go on to derivatives and continuity. All right. So we'll practice this again. I will look for an applet for you. I believe there's an applet out there that lets you practice drawing the derivative on the graph. So I will look up that applet and I will let you know what it is, either by email or in class tomorrow. Okay, let's talk about derivatives and continuity. We want to know when the derivative is continuous and when it's not. And when the function is continuous, does that guarantee that we have a derivative? If you have a derivative, we call that being differentiable. So if the derivative exists at a point, then we say the function is differentiable there. Now, it turns out that if the function is differentiable, if the derivative exists, then it has to be continuous there. And remember that continuity means three things. The function exists, the two-sided limit exists, and the function is equal to the two-sided limit. All right? Function exists, the two-sided limit exists, function equals the derivative. All right? Okay. Now, the reverse is not necessarily true. Just because a function is continuous does not mean it's differentiable. So if it's differentiable, then it's continuous, but the reverse does not work. All right? If differentiable, then continuous. But continuity does not mean differentiability. And I'll give you a counter example to that, which is the absolute value function. It comes down, it is continuous. You can draw the absolute value function in one motion like this. All right, you have the absolute value function in one continuous motion, but it does not have a derivative at the origin because it has a corner. And there's not a unique tangent line there. I mean, if you were to try to balance the tangent line on the corner, where are you going to put it? It could go anywhere. So there's no unique tangent line at the corner. And we saw that in the graph of it earlier, where it had a hole at that corner. And it graphed in two linear line segments, horizontal line segments, one at 1, one at -1. So just because the graph is continuous, that does not mean it's differentiable. But if it is differentiable, then it has to be continuous. So it works in one direction only. All right. Okay. All right. Here's a proof of the theorem that differentiability implies continuity. So if we assume that it is differentiable at A, then we're assuming that f prime at A is the limit as x approaches A of f of x minus f of A over x minus A. We're assuming that that exists and is true. If that's true, we need to show that f of A exists, the limit, the two-sided limit exists, and that they're equal to each other. We have to show those three things to prove it's continuous. By the definition of f prime of A and difference in quotient laws of limits, we know that we can split the limit up in the difference quotient and pull the limit inside the fraction and write the limit as x goes to A of f of x minus the limit as x goes to A of f of A over the limit as x goes to A of x minus A. Now, in order for this to work, we need to show that the limit of f of x is equal to f of A. And to accomplish that, we apply a trick that's called adding 0. There are two things that you're always allowed to do anytime, anywhere, as much or as little as you'd like. They are adding 0 and multiplying by 1. So we want to kind of take a look at this limit of f of x as x approaches A. And what we're going to do is what's called adding 0, where this section right here represents add 0, all right? Because we're subtracting f of A and adding f of A, we're really adding nothing, all right? We're adding 0. Then I can group them with f of x minus f of A together. And then I can multiply by a form of 1, which is x minus A divided by itself. And so I'm building the difference quotient right here, where I started with the limit of f of x. So each of these things on the right side is still equivalent to the limit of f of x. But this lets me split the limit up using limit laws. I can take the limit of this first part times the limit of x minus A plus the limit of x approaches A of f of A using the product and sum laws of limits. I know the first one exists because I assumed it was differentiable, and that means f prime of A exists, so it's differentiable. The second part is going to go to 0 because as x approaches A, I can substitute A for x, and A minus A gives me 0. So I get f of A, and that proves that the limit, the two-sided limit, is equal to f of A. All right. So basically that proves that it's continuous at that point. So where are they not going to be continuous? Corners and cusps. So when you think about a cusp, you think about something that's shaped like this. These are what we call cusps. Like the corners of your teeth. Your teeth are called cuspids or bicuspids because they've got points on them. And those pointy parts where it comes around and makes like little loop things, it's not differentiable at those cusps. And those cusps are the pointy parts right there. All right. So basically, derivatives exist except at corners, cusps, and vertical tangent lines. That's where it won't exist, all right? And these are the graphs of the absolute value of x and x to the 2/3. And if you're not sure why it doesn't exist at the cusp, here is the derivative approaching 0 from the left and the derivative approaching 0 from the right. And you'll see from one direction it goes to negative infinity, and one direction it goes to positive infinity. Those aren't even numbers, so it can't exist, but they also don't agree. So we get nothing. It does not exist there. All right. Vertical tangent lines are the other place where we do not have a derivative existing. So corners, cusps, and vertical tangent lines. So on the graph of x cubed, we have one point at the origin where the graph goes vertical, right there. And where the graph goes vertical, then we do not have a tangent line. Okay. All right. Let's take another look at some interesting functions that are continuous, but one that is not differentiable at the origin. This is kind of a strange function. This is defined for all values of the real numbers. It's continuous over all values of the real numbers, but it does not have a derivative at the origin because the limit from the left and the limit from the right do not equal the same value. All right. Remember, the limit from the left and the limit from the right are both going to be determined by this function because that's what it is except at 0. So you're going to be using that function for the limit from the left and the limit from the right, and it oscillates so rapidly that it doesn't exist. So it is continuous at the origin, but it doesn't have a derivative there because the limit from the left and the limit from the right never settle down to one number. It just keeps oscillating rapidly with decreasing magnitude. All right. The limit from the left and the limit from the right do not exist. All right. Now, that's not always true for piecewise defined functions. Sometimes the limit from the left and the limit from the right do exist, and we want to know what value might cause them to be the same value. So let's see, do I have enough time to do this one? I think I do. All right. Find values for, well, actually, I take that back, for M and B. I think I'm going to skip this one because it would take too long. But in order to prove that this exists, we would have to find the values for M and B that make this continuous and differentiable at 3. So first off, remember your first rule is you have to prove that f of 3 exists. And it does. F of 3, we would use rule 2. And this would give me f of 3 is equal to 3 squared, which equals 9. And then for rule 2, I have to find the limit as x approaches 3 from the left, which is going to be the first rule, x less than 3, mx plus b, equal to some value. And then I've got to find the limit as x approaches 3 from the right, which is going to be the x squared. And this is going to approach the value of 9. All right. So I've got to find values for M and B that would make the limit from the left be 9. And then that would exist because all 3 of them would be the same value. But I don't want to take the time to work all the way through this one this time. So we're going to skip it right now. And if we have time at the end of class, we'll come back to it. Okay. It's more important to talk about higher order derivatives. All right. So what are higher order derivatives? We have first derivative, which is what we've been talking about, but we also have things called second derivative, third derivative, fourth derivative, and so on. So we have lots of derivatives that can be applied to a function, sometimes infinitely many derivatives. When you're talking about a position time graph, The derivative of position is velocity. And the derivative of velocity is called acceleration. So if you want to let your position function be s of t, and this is your position function, then the derivative of s of t is velocity, which we usually write as v of t, all right? Now, velocity also has a derivative, which is acceleration. So the derivative of velocity is acceleration. But then it's like we've done the derivative twice on the derivative of the position, and we have. So we mark that with 2 primes instead of 1. So we have 2 primes, which is the second derivative of position, which is the first derivative of velocity, which gives us acceleration. There's actually another one for the position, velocity, acceleration relationship. The derivative of acceleration is called jerk. So when you take the derivative acceleration, this is a of t, you get the derivative of a of t is equal to the jerk. It's like in your car where you're driving along and somebody floors it and you have that sensation of your head popping back, you getting jerked by the car. That's called the jerk. That's the rate of change of acceleration with respect to time. It's the second derivative of velocity, and it's the third derivative of the position time graph. And we do write 3 tick marks to indicate the third derivative of the position time graph. And then the second derivative of velocity, first derivative of acceleration, and that's what's known as jerk. All right. Now, once we get to the fourth derivative, we kind of give up on the prime notation and we start using a different notation. So here are our derivatives. So let me put the first derivative up here above. So first derivative, we have f prime of x, or just f prime, or y prime of x, or just y prime, or dy dx, or df dx.
+172086882.
Or, let's see, what else do we have? Df of x by dx. All right. So we have these values for the first derivative up here. The second derivative you write with 2 prime marks, or in the d by dx form, you put a 2 between the d and the y and a 2 after the x. Now, what does that mean? The normal notation for this is d squared by dx squared. What that means is you're doing the derivative 2 times with respect to x both times. That's what you interpret it as. The derivative twice with respect to x both times with the 2. All right. So when we're looking at the notation, where you put the 2 sort of determines the meaning of it. So the 2 goes between the d and the y, or the d and the f. And in the denominator, it goes after the x to indicate you're taking the derivative with respect to x both times. When you get into calculus 3, you will have multiple variables. And so you might take the derivative with respect to x and then take the derivative with respect to y. So you could have the derivative of f with respect to x and then with respect to y, which is why we have this notation of dx twice, because that means do it with respect to x, do it with respect to x again. All right. Now, when you get into the third derivative, we have 3 prime marks, which indicate the third derivative. And we use a 3 in Leibniz's notation. All right. When we get to 4, we give up on the tick marks because it's just too many tick marks to keep track of. And instead, we put the 4 in parentheses. And this represents the fourth derivative, all right? Okay. And then this notation is the same. And then once we reach the fourth and the fifth and the nth derivative, we continue with the derivative number in parentheses between the f and the x where the prime notation would have gone. And then we leave that number in the d by dx form. So we only use the prime notation for first, second, and third. What does it really mean? Well, if you're really looking at the third derivative, it means you're taking the derivative of the derivative of the derivative. That's really what it means. The derivative of the derivative of the derivative. So the second derivative with respect to x both times of the first derivative and so forth. That's what you're really doing. Okay. Now let's take a look at a relatively simple one. We want to find the second derivative using our notation that we have right here. So we're going to start by finding f prime of x. And f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all divided by h. All right. So then we can find f of x plus h, which is something squared. Replace it with x plus h. That gives us x squared plus 2hx plus h squared. So we get the limit as h goes to 0 of x squared plus 2hx plus h squared minus x squared all over h. The x squareds cancel. We can reduce the h's over h, and we get the limit as h goes to 0 of 2x plus h, which is equal to 2x. That's our f prime of x. Then if we want to find the second derivative, we repeat the process on that part right there. So we repeat the entire process by repeating it on this function. So f double prime of x is going to be the limit as h goes to 0 of f prime of x plus h minus f prime of x all over h. All right. So if we plug in x plus h into the 2x, we get 2x plus 2h. All over h. The 2x's cancel, and we get the limit as h goes to 0 of 2h over h, which is just 2. So the second derivative is a 2. In other words, it's a constant. All right. Let me show you what this looks like on the graph over here. So we're going to put up x squared first. All right, so there's my graph of x squared. Now I'm going to put up the graph of the derivative. All right, there's the graph of the derivative. Does everybody see where that's the graph of the derivative? Notice that where it has a minimum on the original, I have an x-intercept on the derivative. Now, the derivative of the derivative is going to be a line y equal 2. That's the derivative of the derivative. So this is the second derivative. So what is the slope of this line? It must be 2. All right. We can scroll in a little bit. Make it a little clearer. All right. Okay. And I think all I have left to do are a couple of examples of doing the same thing. But I think, let's see, let's take a look at 12. I think we have enough time to finish 12. I don't know if we have enough time to get to 13. We'll see. The position of a particle along a coordinate axis at time t is given by s of t equals t cubed in meters. Find the function that describes its acceleration at time t, a of t. So remember that a of t is equal to v prime of t, which is the second derivative of position. So I'm taking t cubed and I'm going to find the derivative twice. So first I'm going to do f of x plus h, which is going to be x plus h cubed, which is going to give me x plus h times x plus h times x plus h, which is going to give me x squared plus 2hx plus h squared times x plus h, which gives me x cubed plus hx squared plus 2hx squared. You guys check my algebra. Plus 2h squared x plus h squared x plus h cubed. I think I got it. It should be 1331 from the binomial theorem. All right. And now I'm going to plug that into my difference quotient. So I have the limit as h goes to 0 of f of x plus h minus f of x all over h, which gives me x cubed plus 3hx squared plus 3h squared x plus h cubed minus h or x cubed all over h. And I forgot my limit. All right. The x cubes cancel, and I can factor out the h from each term. And that's going to give me the limit as h goes to 0 of 3x squared plus 3hx plus h squared. When h goes to 0 and I plug that in, the only one that's going to stay is the 3x squared. That's the first derivative. So f prime of x is equal to 3x squared. Then I'm going to repeat the process on that particular term. All right. So to get the second derivative, I have to repeat it. The limit as h goes to 0 of f prime of x plus h minus f prime of x over h. So f prime of x plus h is 3 times x plus h squared, which is 3 times x squared plus 2hx plus h squared. So I have the limit of 3x squared plus 6hx plus 3h squared minus 3x squared all over h. The 3x squareds cancel. I can take an h out of each term in the numerator, and I get the limit as h goes to 0 of 6x plus 3h, which becomes 6x. So my acceleration is equal to 6t, if you want to write it in terms of t, or you could write it as 6x in terms of x.